Hello everyone, today I'm going to talk about photodetectors. So first of all, let's see the contents. We'll start by overview, concept of photodetectors, some types of photodetectors, applications, advantages and disadvantages, Islamization and references. So let's start with the overview. As we can see here, we have the optoelectronics and they involve the light sources such as LEDs and laser diodes and other types, and for optoelectronics they employs light detectors such as solar cell and photodiode. And what do we mean here by involves and employs? There is some devices that convert optical energy into electrical energy, and those are the one that employs. Those are the solar cell and the photodiodes. And there is emitters of photons, and those include the light emitting diodes, this one, and some types of laser, as it can be here seen the laser diode. Before we start our topic, we have to know what is photodetectors, or what is photodetector. Photodetector is a semiconductor device that can convert optical signal into an electrical signal. And what do we mean here by optical signal? There are three theories that are widely used to describe the behavior of the optical signal. The one that we are focusing on here is the one that has been explained by the quantum theory, which is saying that the optical signal consists of discrete units called photons. So how does the photodetector work? The operation of photodetector, just here I'm generally speaking, involves three steps: carrier generation by incident light, carrier transport and or multiplication by whatever current gain mechanism may be present, and interaction of current with the external circuit to provide the output signal. And we'll talk about this more in details when we are going to talk about each type of photodetector. So first of all, we will start with the photoconductor, and as it can be seen, it is the simplest type of photodetector. A photoconductor simply consists of slab of semiconductor with ohmic contacts at both ends of the slab. So let's talk about photoconductor more in details. Let's say this is our photoconductor, and this is usually silicon, and we have here the ohmic contacts. Here we have incident light, and if this incident light is sufficient, we will have electron hole pairs. If we apply electric field, we apply the electric field, and this one, let's say this one will be positive and this one negative. What will happen here to the electron hole pairs is that they will extract, so the electron will move to the positive terminal when the hole will move to the negative terminal. And here we can see the movement of the electric field. Moreover, the device is proportional to the number of electron hole pairs that are generated, which they depend by themselves on the intensity of the light. Another point we didn't mention here is when the photon hits the semiconductor, electron hole pairs are generated either by intrinsic or extrinsic. Okay, say this one is here, and with energy bands. The gain can be measured in the photoconductor, and the formula for the gain is tau 1 over T Rn plus 1 over T Rp. And the tau here representing the carrier lifetime when these both they represent the transit time. The transit time by itself has its own formula, so which is TRN equal UN E. This is for the electron, and for the hole TRP equal L U hole and E. So when the electric field increase or the mobility of the electron increase, the transit time decrease, and when the L increase, and by the way L here it is the length of the device, so when the length of the device increase, the transit time also decrease. Usually in photoconductor there will be thermal noise, and that is due to thermally generated electron holes. So that's why we usually operate the photoconductor at low temperature. Why? Simply just to reduce the thermal noise.
After photoconductor, we will talk now about photodiode. It is basically a p-n junction, and it's operated under reverse bias. When an photon hit the depletion region, this will generate electron hole pairs, and an electric current will flow in the external circuit. To increase the quantum efficiency, the depletion layer must be sufficiently thick. We have here also the PIN photodiode, which is one of the most common photodetector. As it can be seen here, this is the general structure of the PIN photodiode. Here we can see the photon, how it's entering, and here we have anti-reflective coating. The point from having this material is to absorb most of the light. So actually this photon will penetrate inside the semiconductor. The PIN photodiode is 10 times faster than the PN photodiode. The depletion region thickness, which is the intrinsic layer, it can be seen here, can be tailored to optimize the quantum efficiency and the frequency response. Of course, we will come to this concept. We'll try to understand everything in detail. Okay, now we will draw the energy band diagram for the PN junction. So let's say this one is this will be the conduction band, this will be the valence band, and this one is going down. So 1.1 eV, and this one here will be the depletion region. So when photon hits the depletion region, an electron hole pair will be generated. So the electron, if it got enough energy, it will move to a higher level. So, and this happens when HV is bigger than the energy band. If this is the case, then this electron will move from the valence band to the conduction band, and after that, and here also another electron will move. So here the electron is free to move. It will be free to move, free to conduct. That's why it's gonna move to its lower potential energy, and the hole here will move up. In the absence of any light, there will be small current, which is reversed saturation current. and this current will be enhanced by the incident light because we will have additional photocurrent. Before a minute we talked about the PIN photodiode, and we talked how it's 10 times faster than the PM photodiode, and how it's most commonly used. Now we will discuss and we will know why it is so important and why it is faster than the PN photodiode. Okay, let's say that we have the PN junction. We have an area here, call it number 1, and this one will be number 2, and this one will be number 3. This is P and this is N, and they are connected in a reversed bias. This one here, it will be the depletion region, and of course there will be some light, some photons are coming from there. So here will be some generation of electron hole pairs. The electron will move to the positive terminal, and the holes will move to the side of the negative. And here the electrons, because of the diffusion, this is the diffusion area, they are moving this way, and the holes are moving the other side. Here we will have electron hole pair, and they are wandering, they don't know where to go. And that's because there is no potential difference here, it's flat potential energy. If you can see the depletion region, it has the highest potential difference. All the potential difference is in here. And this when this region and this whole region will have no electric field because of flat potential energy. So the question is there a way, is there any way that we can from it increase the depletion region so we will have more current? And this can happen by this can happen by putting intrinsic region. So the junction will be something like this. This will be smaller, the P, this is the P, this is the N, and this is the intrinsic region. So now, as it can be seen, there will be more photons entering. More photons are entering here, and we will have a stronger electric field. Of course, this is also reverse bias. So what we got now from putting what is the benefit from the intrinsic region? Now we are having more electric field, or stronger electric field, and we have a high capture area for photons. Now we are getting more photons in the semiconductor, and because the electric field here is so high, there will be more recombination between the electrons and holes, and that the quantum efficiency will go up. Another benefit we will get from the PIN photodiode is the capacity. Of course, we have a capacity in the PN junction. Usually we have capacity, and I will show it to you in here. Here in this region, as we said, this is the depletion region. This will be positive, and this one negative ions. This is P, this is N, and here we are having the capacitance, and this capacitance we got because of charge migration due to concentration difference. As we know, the capacity is equal to electric field, the area over the depletion region. So when we increase the depletion region, as what happened in the PIN photodiode, when we increase the depletion region, we make it bigger, more photons entering, a stronger electric field. When the depletion region increase, we are tending to have a lower capacity. How this can affect, how can this help us? As we know, the frequency response is equal to 1 over 2 pi RC. So when we are decreasing the capacity, the frequency response is higher. So we are having a faster detector. And of course we are the transit time decreasing. Okay, now let's talk about the metal semiconductor. The metal semiconductor is a type of semiconductor in which a metal comes in close contact with the semiconductor material. The metal here, the metal film, must be very thin to avoid the large reflection and absorption losses. And as for the guarding, to protect from breakdown effects around the metallized area because of the high electric field. Also to protect from the leakage effect. So now let's see what is the energy band diagram looks like for the metal semiconductor. Okay, now we are going to see the energy band diagram for the metal semiconductor. So here we are having the material, and there is plenty of electrons in here, and here there is some discontinuity, and because of it we are having something like a barrier, and this one we are going to call it Schottky barrier. This one is Schottky barrier. This will be easy, and here we will have E. So the electron's movement here is restricted. However, if we connect this one to forward bias, of course this one is N. So if we connect it to forward bias like this, this energy will go up, so it will become, so I will draw it in different color. It will be something like this, and this one also will go up. So here is the new energy band. And it goes, of course, because we are putting more negative charge here, so that's why it goes up. And because of this, the electron here are going to move to this side, and that is because the thermionic emission. This process, we are calling it the moving of the electrons above the or over the barrier. We are calling this as the thermionic emission. However, if we connect it to reverse bias, so let's say this one is reverse bias. Okay, so this energy will go down. It will tend to go down. It will be something like this. And this barrier will become even bigger. So the movement of the electron in here, it will become so restricted, they cannot move at all. However, some tunneling will happen, because here there's plenty of electrons, here there's plenty of electrons, and here there's some vacant states. So some tunneling will happen from here to here. And this will give us a reverse current. Now if I, in some way, if I can reduce the barrier width. So if the barrier width I reduce, I make it less wide. So, and of course it is connected to, this is N, and this is here, bands, and this one is negative. This one is forward bias. If I connect it in forward bias, what will happen is the electron, and here this is the width, the width of the barrier. So we reduce the width of the barrier and we connect it to forward bias. What will happen is we will have here a thermionic emission, and at the same time, because there is also some vacant state here, there is some vacant state, so some tunneling will happen also. So for the forward current, it's coming from primarily from the thermionic emission plus the tunneling, and for the reverse current it's coming from tunneling only. Reaching to application, we will start with the photoconductors. They are used for a wide variety of purposes, all of which require light to determine whether a device should be on, off, or set to a particular position. They are responsible for turning street lights on, off, and measuring the amount of light that a camera picks up. It is used in some types of alarms and clocks. PN or PIN photodiodes are used in consumer electronics devices, such as compact displays, smoke detectors, and the receivers for infrared remote control devices, which is used to control equipment from television to air conditioners. PIN diodes are mostly used in optical communication and lighting regulation. As for the metal semiconductor, they are useful in voltage clamping application, prevention of transistor saturation. It can naturally be used as general purpose rectifier, and they are used for radio frequency application. And Schottky diodes are similarly very good as radio frequency detectors. However, in terms of radio frequency application, it is particularly useful because of its high switching speed and high frequency capability. Schottky diodes are similarly very good as radio frequency detector, as their low capacitance and forward voltage drop enable them to detect signal which an ordinarily PN junction wouldn't see. As for the advantages and the disadvantages, for the photoconductor, they are completely dependent on how much light they receive.
They are small enough to fit into virtually any electronic device and are used all around the world as a basic component in many electrical systems. Photoresistors have a simple design. As for the disadvantages, they cannot detect low light sometimes and is slow to respond to new levels of light. PIN photodiode, the advantages, are capable of operating speeds up to 10 MHz. They have higher quantum efficiency than PIN diodes, and we have discussed why. They exhibit higher sensitivity and responsivity. As for the disadvantage, there is no amplification in PIN diodes. For the metal semiconductor, they have, for advantages, fast switching. Schottky diodes have extremely fast switching ability. They are used as a switching elements in generators, detectors, motor driver circuit, RF circuit, and a variety of other circuits. However, the main disadvantage of the Schottky diode is that it has a relatively high reverse current. Here we can see the gain and the response time for the photodetector that we discussed, the photoconductor, gain, the photodiode, etc. And here is the response time. For Islamization, due to the fact that the photodetector basically works on lights and electrons, we may try to find a relation between what is there in the Quran and what has been discovered by science. The question is, did the Quran mention anything about electrons or light? We will try to find some answer. Prior to the Quran, philosophers thought that the atom was the smallest indivisible component of matter. However, today we know that this was false. Atoms are composed of electrons, neutrons, and protons. And lately, it turned out that those neutrons and protons are made of quarks. However, 1400 years ago, the Quran contradicted the common knowledge of the time. It stated that the atom is not the smallest part. In the ayah saying, He is the knower of the unseen, whom not an atom's weight lose, either in the heavens or in the earth, nor is there anything smaller or larger than that which is not in a clear book. In the Quran also, in the verse 1061, whatever you may be doing and whatever portion you may be reciting from the Quran, and whatever deed you may be doing, we, Allah, do witness when you are doing it. And nothing is hidden from your Lord so much as the weight of an atom on earth and in heaven, not less than that, nor more, what is written in a clear record. Other than that, the speed of the light has been mentioned in the Quran, and to show this idea, or to clear this idea, I will show you a small video. That is all. Thank you for listening.